We are going to discuss about the entanglement structure of a quantum state which is prepared on multiple copies of torus. So just for a reference, I have given a figure here which consists of a three-dimensional manifold which has 3 torus boundaries. So the most of the introduction of this seminar is given from the Witten's paper on quantum field theory and Jones polynomial, and I will give some results of these 3 papers. This last one is our paper, and 2 of the collaborators, Vivek and Lata, are already here. So let's start. So the quantum field theory in this setup is a 3-dimensional Chern-Simons theory. The manifold is 3-dimensional, which is oriented and a closed manifold, I mean without boundary. The gauge group is a compact simple group, which is denoted by G, and the action, the Chern-Simons action is given here. This coefficient here is the coupling constant, which is also called the Chern-Simons level. And for the compact simple group, this is an integer. As you can see here, there is no use of metric in the action. So this theory is a topological theory. Also, there are some gauge invariant observables which are called Wilson lines or Wilson loops. So we can define the Wilson loop by taking a oriented closed curve in this 3-dimensional manifold and assign a representation R of the gauge group G, take the holonomy, and the trace in the representation R gives a Wilson loop. Okay, so so one can compute the Chern-Simons partition function, or in other same way, the expectation value of the Wilson lines using this integral, where the integral is over all the gauge connections modulo the gauge transformation. So if we put a Wilson line in the 3-dimensional manifold with representation R, then this integral will give the partition function of the manifold M in presence of the Wilson line. Okay. Similarly, if we have like two separate Wilson lines, then the integral will give the partition function of the manifold in the presence of these 2 Wilson lines. We can also have a Wilson line in the trivial 0 representation, or equivalently no Wilson line. Then this integral will give simply the partition function of the manifold. Okay. Now, since this action was a topological action, this integral will give the partition function, which will be now a topological invariant of the manifold M. Okay. Okay. So yeah. So in order to compute these integrals, one way is to simply evaluate the integral by integrating over all the gauge connections. There's another way which is called the canonical quantization, which can be done using the technique of surgery on these manifolds, which I'm going to explain next. Okay, so this is what canonical quantization means. So if we have a manifold M which has some boundary sigma, then the canonical quantization on this manifold will give a Hilbert space on this boundary. So what we do is we take the manifold and cut this manifold along a Riemann surface sigma. Okay. So basically this will cut the manifold into 2 parts, and if we do this canonical quantization on this manifold, it will associate a Hilbert space on this boundary sigma. so we have two parts. We have broken the manifold into two parts. We do the path integral on these two manifolds. So path integral on this manifold will give some Hilbert space. Path integral on this manifold will give some Hilbert space. Now since this we have cut the manifold along this surface sigma, these two manifolds have the same boundary but with opposite orientation.
If I do the path integral, then I should get a single wave function. Why am I getting a Hilbert space worth of?
Yes. So you will get a vector in this Hilbert space, right?
Yeah. Right. So what do you mean by saying that the path integral gives you a Hilbert space? I thought the path integral should give you just a single sketch, like psi1.
Yeah. So it will give a yes, of course. It will be a state in this Hilbert space. So each boundary sigma, so we will get associated Hilbert space, and if you do the Chern-Simons path integral, it will give a state in this Hilbert space. Right? So this will give some state. We don't know what is the state, but it will give some state psi1 here, and here we'll get another state psi2. Now since these two Hilbert spaces are like canonical dual, there is a notion of inner product between these two states. So we can compute the inner product. And in fact, so basically this inner product will give the partition function of the original manifold. Yeah, so this one. So we had this manifold M. We have cut this manifold along a Riemann surface. We do the path integral, and this gives a state here, a vector here. It gives a vector here. When we take the inner product, this is equivalent to gluing these two parts to get back the original manifold, and this inner product will give the Chern-Simons partition function of this manifold.
What do you mean the two Hilbert spaces are canonically dual?
I think it means that there's a notion of inner product. And take the inner product from the two vectors.
Are they're not exactly the same Hilbert space?
Mm.
Some orientation difference? I mean,
Yeah. So
it's a Hilbert space of Chern-Simons on the same two manifolds.
right.
Sorry, I missed the beginning. Sigma is what?
Sigma is the Riemann surface.
Yeah, Riemann surface. The whole manifold is 3 vectors.
Yes.
So,
And
so is there a clear notion of the Hilbert space of Chern-Simons on a given two-dimensional manifold, or is there some orientation which we are considering? I mean, both sides you get sigma, right?
yes.
So is it the same Hilbert space or?
Yeah, I think that they're the same Hilbert space.
They're the same Hilbert.
They're the same Hilbert space, but because of these different orientations, you can define a bra here and take the inner product.
So the Hilbert space knows about the orientation somehow, or not?
No.
Okay.
I'm a little confused by Hilbert space. On sigma, if I do this pattern testing, you just get a state.
Yeah. So this is the state which we get.
You get one state.
One state,
You can't
yes.
reproduce all
No.
states in this
No.
space. You get one.
We get one state.
Yeah, but you know, he might be saying this, that if you put lots of different insertions, let's say lots of different Wilson lines in one, you produce a whole Hilbert space.
Right.
You put a lot of different Wilson lines in two, you produce a whole other Hilbert space. I wanted to understand whether those two Hilbert spaces were isomorphic or exactly the same, or whether there was any difference between them.
I think probably there's a CPT conjugation, right? I mean, if you do the path integral from minus infinity up to infinity. So the two are the same, but more correctly they are related to a CPT or something, which is why
Okay.
you can then define the inner product. Right?
Okay.
But they don't have to be. M1 and M2 can be totally different.
Well, I think Shiraz's example, just for simplicity.
Yeah, it doesn't even matter whether they're different or not, as long as they cut on the same thing. But I was wondering whether cutting this way and cutting that way makes them complicated, whatever that means.
I think it does.
What precisely does it mean?
I think
What do you mean by
it's
cutting this way?
This way and that. I mean,
My feeling is, I mean, usually at least, this is like the Hartle-Hawking wave function. So usually, the two are related by CPT. In one case, you generate the state from minus infinity up, and in the other case from the infinity down. And so there's time reversal. But the more correct thing is CPT, which you are seeing here because T is changing your orientation.
Oh, okay.
yeah, and this probably is related to the following confusion. product should be linear on psi 1 and anti-linear on psi 2. And this is probably your point, right?
Yeah, because what the other one is giving is psi star.
Yeah.
You know,
Yeah.
which is because the way he acts is
Involves
star.
the star, yeah.
Okay.
So that's sort of,
Yeah.
Okay, so this was the case when we simply glued the two pieces together. We can also take one of the boundaries and do some diffeomorphism on this boundary, and then glue them back. So this procedure will give a different manifold, which will be this is topologically different from the original manifold M. And
so you diffeomorphism on the
on one of the boundaries, yeah.
But since you told us that the action, at least for Chern-Simons, doesn't care about the next wave, will the wave function change?
Yes, so this diffeomorphism will act on that state, and it will give a different state.
Let's say the sigma was a torus, then you can exchange the two factors.
Yeah.
The wave function which was depending on this and this,
Mm.
rather than that. But once you glue, if you do diffeomorphism on one but not on the other, you glue, you get a completely different function. Yeah, well, because for instance, one
Mm.
cycle of the torus could be filled in, not the other.
Yeah. So I have an example of what torus.
So what will this matrix match when you redo the path? So there is some path integral in the manifold.
You get a totally different topology for your net free manifold. Imagine that the right hand, I'm sorry, you should
No, it's
let
okay.
me just go on. Imagine the right hand side was a solid torus. So one of the cycles of the torus is filled in, and the other one is not. Okay? Now imagine the left hand side was also a solid torus. One of the cycles is filled in, the other one is not. If you glue, in one way you're joining the two non-filled in cycles and the two filled in cycles. The other way you're joining the non-filled in with the filled in and the filled in with the non-filled in. It's totally different free manifold topology.
Just to tell you the path integral, we're doing a path integral with over some manifold with this one boundary
Mhm.
using an action which doesn't care about the metric.
Yes.
So where does the metric dependence come in the resulting value of the path integral? Or even the boundary condition doesn't.
It's to the topology of the manifold.
Yeah, so that diffeomorphism changes. Oh, it changes the topology of the right hand side.
Like it exchanges the two cycles.
Yeah.
After the loop.
See, the A cycle is filled in, the B cycle is not.
I mean, this non-dependence on the metric will be being independent from small diffeomorphism. The large diffeomorphisms are still
So by large grade, you mean those which won't vanish at the boundary?
the ones that are not connected identically. I mean, there's a problem for a compact thing, you can define them as things that are not connected particularly by identity.
So, I mean, the action is still independent. On a closed manifold, it doesn't matter, right?
It is the boundary part of the action.
Yeah.
And they give it something like boundary part, which however is the
But I mean, here the action is able to create something.
So the wave function is a function of the two velocities. That's in my example. The boundary is the torus. The wave function is a function of the velocity on the x cycle and the velocity on the y. You have one function of the velocity on the x and y. You take x and y, you get different functions.
one, yeah, dependence on one velocity was real because it was supported only on the zero velocity because one was that was contacted. So only about the contacted. So clearly there is an asymmetry between these two variables. So they want to be dependent. And the large diffeomorphism is able to close to
Okay. So yeah. So this is the part where there is no diffeomorphism, and we just cut and glue them back and get the partition function. And if we do the diffeomorphism, then on this boundary, then the state will change to some other state. That will depend on what is the diffeomorphism operator. And when glue, we'll have topologically different manifold whose partition function can be obtained by simply taking the inner product like this. Okay, so this is how we do the surgery on the manifold M. So let's take a oriented closed curve in the manifold M and take a tubular neighborhood around this curve and take it out from the manifold M. So this manifold will break into two parts. One is a solid torus and another is a manifold which has torus boundary. Both of them will have the same torus boundary T2. So this was a simple loop. We can also have some complicated knot embedded in M, and if we take the tubular neighborhood similar to this, we'll get two parts. So this is the part where let's say this Riemann surface is a torus T2. So this torus will have two cycles: the A cycle, which is contractible in the solid torus, and the cycle B, which is non-contractible. So this is the result of Wallenday, that if we put a Wilson line in the bulk of solid torus running parallel to this B cycle in representation R, then the Chern-Simons path integral will give a state on the boundary T2, which let's say denoted by some R. Okay. Siegel and Wallenday.
This was before Wilson's paper?
Yeah. And moreover, the representation which we can put here will depend on the gauge group and also the level K. So for a given group G and Chern-Simons level K, only certain representations are allowed. And these representations are the integrable representations of the affine extension of the group G with the level K. So the Hilbert space which we can obtain for sigma is equal to T2 is a finite dimensional Hilbert space, and is spanned by the integrable representations. So what is an integrable representation? And also, so this basis is also called as the Wallenday basis. So this is the definition of the integrable representations. So if we take simply SU2, then with level K, then the integrable representations are all the representations with the spin 0, half, up to K by 2. Similarly, we can also obtain the integrable representations for the SUN group, where the integrability condition is given like this. For a general compact simple group with rank R, this is the integrability condition. So given a value of K and given the group, that is given the values of these thetas, we can obtain what are the possible representations allowed.
Can I ask, suppose I put a non-integrable Wilson line, some higher representation Wilson line in the top?
I think that will correspond to your zero vector, the vector corresponding to the zero representation.
Every Wilson line? I thought it would be.
Which is not an integrable representation.
So I could do the path integral with anything I want?
Yes.
So suppose I choose to do the path integral with K by 2 plus alpha.
Yeah.
Okay.
Yeah.
What will I get?
You will get a state which is the state when you do the path integral using the zero representation.
Irrespective of what alpha is?
What is alpha?
I mean J is equal to K by 2 plus alpha.
Yes. I think. Right? Huh?
I think you get some linear combination.
What if you combine like two particles, like, I could take two things in this, two Wilson lines in the spin half representation. Suppose I go to bigger and K over 2 like that.
I was wondering whether it is exactly like alpha, or is it more? I mean, it's certainly true that K by 2 will give you K by 2 plus 1, or half will give you 0. So then will it just repeat completely, or is it more complicated? It just repeats. Yeah. Okay. Yeah. To the lower one, and in a repeating pattern, right?
Oh, okay. one?
Conjugation matrix will be diagonal on this basis.
I didn't even understand it. What is complication?
So, suppose you have a CSP. Now, when you have some operator phi, you can ask what is the conjugate of that operator. But the definition of conjugate is that phi and conjugate of phi has non-trivial two-point function, non-zero two-point function, which is, you want to diagonal. It is a standard diagonal form. And it might be that you are choosing a basis of.
Now, see, how do you know that it has a state with definite basis?
How do you know that the conjugate is diagonal from this basis?
It's an operator with given scaling diagonal.
So, I thought the question was, how do you know the inner product is diagonal of this
You
torus
know
thing?
inner product is getting some state. He is getting some state. He is getting some operator on the boundary. Now, how do you know that in this basis of operators? You can have different basis, right? That is different set of operators. How do you know that in this basis this conjugation matrix is actually diagonal, which is as per the definition of diagonal basis?
But that, if you look at the inner product, it would be the path integral on x2 times x1 with 2 variables. You calculate it. Right. R and R bar are noted by x.
Okay, so you are saying that if I calculate the inner product, then
You compute it as a path integral with tensor.
But in different way, so you could put that as two and between questions.
Doubt it.
Okay, so this is an example of how we can do the diffeomorphism on the torus. So there are two types of transformation diffeomorphisms which you can do on the torus. So these are called the S and T, which are the generators of the modular group SL2Z. So this S transformation exchanges the two cycles, like Shiraz was saying. So
you
you
want PSL2 or SL?
SL,
You don't want the T part.
no.
So then ST does all the job.
Yes, I think
What is
the yeah.
What is this PSL2 and SL2?
What out by V2?
The reverse is the nature of tau of this dash on the vector.
I.
But does S square? See, SL2 is square no one. No, just take that as S square. You get minus. That's the essence.
S square is 1 for E.
I think S square is this charge conjugation matrix, right? For a general.
Just take equal to S and then just do it twice, you get minus.
Oh, this one?
No, if I just take that definition of S
Uh,
and act on it twice.
oh, okay.
Minus. But then you're writing S squared into plus.
S square is, I think, yeah, C, and S to the power 4 is 1
Yes.
for a right for a general group. For SUN, this is true. S square is identity. Okay, so this S transformation exchanges the two cycles, and so this is a diffeomorphism. So the action of a diffeomorphism, some K acting on the state. This is a one linear basis, can be given as some J, Kij, Vj. So these transformations can be written in one linear basis with these the matrix elements are given like this. For SU2, this is a well-known matrix, and the elements are given like this.
That S doesn't make this square
S square is 1 for SUN groups. In general, they satisfy this condition.
SUN, your R doesn't go to R bar and C.
What for SUN?
Representation R
Uh,
will go to R bar under C.
So that depends. So for SUN with level k, you have to take all the integrable representations and form the matrix.
Can we just write down the transformation rule of the state R and that with external modular rule? So how does S interact? Is it that state J goes to S J1 J2 times state J?
You mean this one? So this is how diffeomorphism acts on the Valide basis. K is the diffeomorphism operator. It acts on the Valide basis, which can be given as a combination of the Valide basis. So these are the matrix. Yeah.
So what is the action of C on the representation? Because you're saying S squared is equal to C for general rule. But then for SUN, C becomes 1.
Yes.
What's confusing, at least some people confusing me, is that if C is charge conjugation, then a fundamental should go to an antibody. Unless he's by C means something different than what I normally do.
Okay.
Are you sure that the statement is not just true for SU2?
For SU2 it is. It is true for SU2.
For SU2 it's certainly true.
Yeah.
That I think.
Okay. So now here is the way of how we can compute the partition functions for different manifolds. So if we have a solid torus can be written as disk times S1. We also know that if we have two disks, each having S1 boundary, we can glue these disks around the S1 boundary to get a different manifold S2. So using these two, if we take two solid torus having T2 boundary, we can glue them along T2 to get S2 cross S1. Okay. We also have seen that if we have a solid torus with a Wilson line in representation R running parallel to the B cycle, then the Chern-Simons path integral gives a state R. Okay. And also, no Wilson line means is like equivalent to saying that Wilson line in the zero representation. So if we take two solid torus with no Wilson line or Wilson line in the zero representation, then we do the path integral. So we'll get the vector 0 and 0 on this part and this part. And when we glue them, we take the inner product of these two vectors, and that will give the partition function of the manifold, which is obtained after going, which is S2 cross S1. Hence, the partition function for S2 cross S1 is like 1. So this Valide basis, this basis is a normalized basis.
I think you're using the fact that you know that on S2 there is a unique state. So then you interpret this as straight, you just probably look at it.
So all are associated on the.
Yeah, for any other manifold you'd have a hard time. This one is just Hilbert.
No, I mean
Any representation will be hard.
So we can use the same procedure to get the partition function for S3. So for to get S3, we take two copies of solid torus. Yeah.
So has some question been answered? I mean, so how does the diffeomorphism act on the second stage?
Mm.
So presumably it's because there is a Chern-Simons action, but there's also an insertion of Wilson lines. So without that insertion of Wilson lines, this K will not act on that. If there is nothing at all, then K will not act. Is that right? I mean, if you have some state and if you have some other state, then how does, unless
No,
there
but
is a boundary term will like
here there is no Wilson line. So you can.
We should go on, but I think also they will not agree with, right, the following. When you do the path integral and you end on a T2, you get a unique wave function. And it doesn't matter which you call the A and which you call the B cycle. Two people may disagree, but they will both agree that you have a unique wave function that's what I would, that's how I would.
There is one comment on that.
Yeah.
The Hilbert space on T2 is finite dimension. You don't get unique wave function. Okay. Doing different things in the way can give you different.
No, but if you do the same wave function and end on a T2, whether you call something the A cycle or something the B cycle, doesn't make a difference.
Yeah, that's defined canonically because of the top.
Yeah.
Then you have a different, then you can make a difference. Once you specify that this was going to glue
Yeah.
things,
Then,
then
in the,
there is a difference.
right, then in the after the gluing, you will get a difference.
Yeah, but just by one more point. In the manifold.
I mean, I'm sorry, I'm very remedial in my knowledge.
But suppose think of the manifold itself without reference to any other manifold.
Yes.
In one of the cycles is distinguished from the other because it can be shrunk to nothing within the manifold. So you get a dependence on the Holomy of that cycle and dependence on the Holomy of the other cycle. The two cycles are not equivalent. Even without a Wilson line. Because geometrically they equal. So you can say that you're getting dependence on the shrinkable cycle that's this one and the unshrinkable cycle of that. I mean, just not that I disagree with anything except that.
No, maybe I understand you. Okay, go. I see. Okay. Okay, yeah, I see.
So you can be supported at 0 on the shrinkable cycle, right?
Yeah.
WB.
Sorry.
So here we do the S transformation on the second torus, and when we glue them along the torus boundary, we will get S3. Okay. So if we had two copies of solid torus, we do the S transformation on one of them and glue them. So we'll get we can compute the inner product like 0 and this diffeomorphism acting on this 0 state, which is given here. So which is simply the S00 element of the S matrix. Okay. And we know that this gluing gives the manifold S3, hence the partition function of S3 is simply S00. Now what we can do is, instead of just taking two solid torus, we can put a Wilson line in one of the solid torus in representation R. When we do the S transformation and glue, so this basically this Wilson line will become the A cycle, which is simply a circle, and we'll get the manifold which is S3 and a circle, or which we call as a knot, embedded in this manifold. And this, if we compute the, so this will be S acting on the representation R, so which will be the S0R element of the S matrix. We can also take two Wilson lines on both in the bulk of both the solid torus. When we do the S transformation, so you can see that when we do the S transformation here, the Wilson line will become a different cycle, and when we glue them, so this Wilson line will be linked to the other one. So this gives a Hopf link. This is the Hopf link. So this will give a manifold S3 with a Hopf link embedded in this, and the inner product, which is like SR2, will be simply the R1, R2 element of the S matrix. Okay. Yeah, so I have again, this is again the surgery on S3. So we take a knot, or we can take this is an unknot in this S3. Take a tubular.
Let's make sure I'm understanding the concept. And you say it this way around. The way I would think of it is you take the knot that you want and you do the surgery that is required to make it a bunch of Wilson lines on a S2 tensor.
Yes.
And then you redraw it.
Yes. So we take a tubular neighborhood, and when we cut it out, we'll get two manifolds with the same torus boundaries. And you can put some complicated knot here and do the surgery like this, and you will get, so this manifold, one part is the solid torus, which corresponds to the removal of this knot, and the remaining part is called as the knot complement. So this is a three-dimensional manifold with torus boundary. Okay. Okay, so these are the partition functions which you can compute for S3 manifold. And in fact, the Witten's work gives a connection between the knot invariants and these partition functions. And the explicit results I have written here. So these are the S3 partition functions. So if you take SU2 group with spin half representation and compute the partition function of S3 in presence of a knot, it can be matched with the Jones polynomial of that knot K with this realization. Yeah.
So in that knot, which you had,
Hmm.
you remove the knot and there was a torus.
Yeah.
You do a diffeomorphism before patching it up such that it becomes an unknot. Suppose
Here?
you load it, yes, in the second example.
Yeah. No. So okay. So this is you can think of the solid torus is something like I don't know how to something like
Indeed.
Yeah. I mean
So you have the solid torus and knotted and it's complementary.
yes.
So if I stuck it as it is,
Hmm.
as I've taken it out,
Hmm.
I get that.
Yeah. You
knot
get some
surface.
complicated solid torus like this.
And there is a Wilson line along this.
There's a, if you put a Wilson line here, then you will get a Wilson line in this part,
In
the solid torus.
Can I do a diffeomorphism before patching up such that I end up with an unknot?
So
Three dimensions.
yeah, there is no diffeomorphism that can. This is trefoil which will give trefoil to a knot. Hmm.
So although the topology is different, it will not be able to unknot the knot.
Yeah.
So what was the conclusion of this? Like, can you compute this? How do you compute this? Trefoil.
Yes. So you compute the Chern-Simons part integral here in presence of this trefoil with some representation R.
Like how do you? I thought the procedure for computing it was to relate it to something simple.
Yes.
So how are you going? I think that's what I want to ask. How are you relating it to something?
Yes, so actually this this can be done using the Witten paper has this what is that called? Yes, key relation. So you can try to break it into, so you can use the Reed-Master moves to make the undercrossing as overcrossing.
Okay. So you derive the scheme relations and then forget about the Chern-Simons.
Yeah,
Just use
yeah.
the scheme.
Yes.
Is that right?
So this is yeah. So this is the Jones polynomial. If you take the SU2 group with some representation n by 2 and compute the Chern-Simons partition function, you will get a colored Jones polynomial with some say index n. You can also take SUN group with fundamental representation, which will give Holmes-like polynomial. We can also take SON group with fundamental representation, which will give a Kaufman polynomial. In general, you take any group G with level K and some representation R, and you can define the variable Q like this, where Y is the dual coefficient number of the group G, and it will give you some invariant, which will be like not invariant.
And are these more useful in distinguishing knots than the Jones polynomial?
Yeah, so these are like, this is more effective than this is more effective than this. Yeah, because this is more informative. This is a variable, this is a polynomial in two variables, Q and A. Okay, so we have seen this is the knot complement manifold with torus boundary, and we want to construct a quantum state on this boundary. We know that if the boundary is torus, then the Hilbert space is a finite dimensional space which is spanned by the Valinde basis, or in terms of the basis of the integrable representations. So any state psi on this boundary can be written in some linear combination of this Valinde basis like this. So these are some complex coefficients, but as of now, we don't know what are these coefficients. So this is the way to compute these coefficients. So take this knot complement and take a solid torus with a Wilson line in representation in some representation Rm and glue them back. So this will give a partition function of S3 in presence of the knot K, and this Wilson line, so I have not drawn correctly, so this Wilson line is like this one. Okay. So take this Wilson line and then glue them back. So this will give partition the manifold S3 with this sort of Wilson line, right? So this is the state which is on boundary of this manifold, and on the boundary of this manifold we have this state. So when we glue them together, we can take the inner product, and using this inner product we can fix the coefficients, which will be, right, this coefficient can be given like this inner product, and this inner product is nothing but the knot invariant of this knot K.
I see. And can you practically, like for instance, when you say we compute the state on the left hand side,
Yeah.
can one practically do this in some way? Is this a formal thing or something you can actually do in some basis?
I mean, for this manifold, you can always obtain the quantum state, but
Yeah, and how would you do it? Suppose I wanted to ask you, you've got this torus in this knotted thing. You remove that from an S3. Now I want you to find for me the state on that T3. How would you do it?
you need to know these coefficients.
But
Right.
then you're going to use that the partition function is this, is the trap, is the answer. Start. This I understand. But I wanted to know direction.
So for SU2 group, this state psi will be simply summation over I, the Jones polynomial of this knot times the states Ri, right? So in this way we can fix the quantum state.
This is sort of by definition, right? Because
Yeah.
you take the inner product with Ri and that gives you the result.
Yes. So
No.
no, you can use any group here. So all you need is the information about this coefficients, which from the knot theory you already know, the Holmfly and colored Jones.
So Valente basis will be the statement that conformal blocks on a torus are labeled by irreducible representation. Or irreducible representation. So that's all. Right. No, I don't. I was just like without yeah. I mean, I don't know.
Yeah. So this was an example where we had a single knot. You can also have more than one knot. For example, this is a Hopf link where two knots are linked. You can do the similar exercise. You can take the tubular neighborhood, remove from S3. Now you will get a manifold which has two torus boundaries which are linked together. Okay? And the total Hilbert space in this case will be simply the tensor product of the Hilbert space or each torus. And the state, the quantum state on this boundary, which consists of two torus, can be written as some coefficients times the product of two bases. Okay? And using the similar exercise, you can try to put Wilson lines and glue them back. You will find that these coefficients are exactly the Hopf-link invariants.
You get this SAD because you do surgery to make this
Yes.
two loops on S2 tensor.
Yes. Well, this is exactly the Hopf-link invariant which comes here. We can also do similar exercise for n-component links. This is a two-component link, which when you have n-component link, you can just put the Wilson line in each of the torus boundary, glue them back, and you can obtain a quantum state. I mean, you can fix these coefficients by the gluing procedure. So a general quantum state on n copies of torus can be written like this, where these coefficients are known. Now what we can do is, we can try to study the entanglement structure on the boundary by tracing out a subset of these Hilbert spaces. So if it is an n component link, the Hilbert space is a n copies of torus T2. You can try to like trace out n minus m copies, and it will assign entanglement structure on this link state.
Right. So what, sorry, let me understand what you're trying. So you've got a Chern-Simons theory with a boundary which is n copies of T2 topologically.
Yes.
Not necessarily, yeah, they could be intertwined with
Yes,
each other.
yes, yes.
So topologically it's n copies of T2, and you want to find the entanglement entropy of m of them with n minus m.
Yes.
Right?
Yes.
That's a little bit.
So I just given a slide on how to compute the various entanglement measures. So given a given a system with Hilbert space H, you can bipartition this Hilbert space H into two parts, and you can define a quantum state in this Hilbert space, and you can compute the total density matrix using this formula, and you can trace out this part, and it will give you a reduced density matrix, right? Using this reduced density matrix, we can compute many entanglement measures like von Neumann entropy, Rayleigh entropy, and so on. Okay. Yeah. So here we can do the same exercise. We can compute the entanglement of m copies of the Hilbert space with the remaining n minus m copies, and we can compute, in principle, we can compute the Rayleigh entropy. So here are some of the results which have been obtained using this in this setup. So if we take the SU2 group, we know that the dimension of Hilbert space is k+1. And for Hoeffling, the entropy comes out to be maximum, which is equal to the dimension of Hilbert space. So the Rayleigh entropy is independent of the Rayleigh index, and it comes out to be log of k+1, which is the maximum entropy.
Just to be totally clear, if we first start with S2 times S1,
Oh yes.
and I take two Wilson lines around the S1, not
Okay.
linked,
Okay.
and I cut open the torus there. There will the entanglement entropy be 0? Because it's just a product. Okay.
Yeah, you mean so you cut this part here and here, right?
I think S2 times S1, I took two Wilson lines going on in time.
Yes.
Then I cut the tori.
Yeah, yeah. That will give zero entropy.
And even if I put as a Gaussian, I see, but in the absolutely,
You would say you compute the state by inserting, general basis states.
yes,
RM and RM would be supported on a delta.
yes.
And then so the state would
So
be.
you say it will be like 1 by k, a log k, log dimension. Interesting.
The general feature of this case is you get extra entanglement from Gauss's law.
This is the only the pure contribution.
Yeah.
Pure this one.
Not the extracted. Anyway, yeah.
I do. In here, the dimension of Hilbert space would be k squared. Well, let's say, because it would be torus times torus.
Yeah.
But you would get log of k.
Yeah.
Okay. Yeah. Okay, thank you. Now I'm getting sorry.
What happens if you rotate more?
Sorry?
You should say, because it might be interesting if you actually think about what's extractable, then you can't extract a lot. And I'm saying that that might get linked to the integral. Anyway.
Yeah. So here it is coming out to be log k because of this invariant. So this is a unitary matrix. So if we compute the density matrix will be reduced density matrix will be identity.
So I think confused. Why is division of HT2 is k plus 1? As you said, there are k square, right?
No, for a
No, no,
single-
for a single, for a single torus. Yeah.
for a single.
What happens if you have more and more rotations around this?
Here,
Not a happening, but two more rotations.
you mean like this? I mean, like this? Yeah. So it will be less than this. The entropy for this will be less than log of k plus 1.
The number of
Yeah, yeah, yeah. So we'll come to that. There is a periodicity here. Yeah, we'll come to that slide.
Sorry, I think you answered this, but just remedial question before you go to the complicated thing. On S3, if you have two unlinks, then you say the entanglement entropy between those two is 0. And just help me understand, give me the proof for that.
So this state can be written as a separable state because the link invariant will be product of the two link invariants, product of the two not invariants. So this state can be separated.
What's the entanglement question? Presumably you cut the S3 in half and you get the S3 and you have some S3. What's entanglement? Sorry, I'm not following
So you've got an S3 and you've got a Wilson line. Then you cut out a little tube around each of those. Now we are talking about, we've got S3 with two little tubes cut out. And those two tubes are not linked. And the question is, now you've got the Hilbert space on the boundary of one tube, entangling with the Hilbert space boundary of the other tube. You've got a state. You could bring the entanglement entropy of this state. Okay, so the whole Hilbert space is k plus 1 square dimension.
Yes.
Each Hilbert space is k plus 1 times k plus 1.
Right.
The maximum possible entanglement entropy is log k plus 1. Minimum possible entanglement entropy is 0. And we are assuming that in the case where it's unlinked, you get 0, and in the case where it's linked, you get log k.
Yes.
And the unlinked to get 0 entry completely understood. Okay.
So this state psi, we know that if we have like in this case, for summation over whatever
Can
AB.
you do this simpler?
Yeah. So we know that this for SU2 group, this is the Jones polynomial, right? When the two knots carry representation A and B times AB. So if you take two circles which are separated, AB, so this JAB will be, so they are not linked. So it will be given as the not invariant for this knot times the not invariant for this B. So this becomes a product state.
Thank you.
So
So the fact that product of two will
yeah. It's a,
expectation value product is product of a
yes.
Again, I can't quite visualize it, but how do you meet your Gauss law constraint? Where do you cut your two tubes? When you cut the two, you have two tubes at that constant time.
You're thinking of the quantization such that Q is space. So, Gauss law, how does it say?
Is there an equal time solution?
Now you could, if you want, take that cube which is a torus and slice it either this way.
Just because for entanglement using an instant of time, and then you have to ask, right? Okay, so what is the instant of time in this?
So the full field theory is 3-dimensional and the cube is your space. That's your secret that. You've got a Hilbert space on this cube, T2, and you're computing the entanglement of the state on this T2 with the state on that. So if you think of this cube as being used.
And what is it two disconnected components? What's the topology of each disconnected component?
Space.
So then you probably just need to Gauss's law constraint on how we can go further. So each is a disconnected component, right?
But they could be linked. The components could be linked.
Yeah, but if you have a basically two disconnected manifolds, you have to use the dimension.
So there's not even charge going through it.
No, so that must be the case. There is some, I don't know, can't quite picture it, I'm sorry. If
don't know about
Abhijit gave a flavor.
S2 process.
Because then you have things which are not. That's what the right? And then once you have Wilson lines inserted, the only non-zero answers they are going to get when they are conjugate, I mean R and R bar, right? Not any other difference. So the state would be 0 0 plus 1 1 plus 2 2. That's an entanglement state.
Clearly maximally. It's like a bell curve.
Come back to this. How are you slicing here to get the instant line? Just along the S1?
Along at a given time.
S1, then you
One
have
S.
S2, when your two Wilson lines going through, you can get it.
Yeah.
So there it's clear.
Yeah.
I mean, why it's exactly that, but okay, that's more.
Yeah.
Each representation of it is
Yeah. And the exact question that they were asking is we slice out those tubes. So there aren't even Wilson. It's just hollow tube. There is S2 times S1 with two hollow tubes sliced out. So now the way we calculate it is I can suppose I filled in the thing with an R here. Then I have to fill the other guy with an R. That's the only thing that gives me an answer. So, but filling this in with the R is taking the inner product with the state R. Filling this into the R bar, inner product with state R. And we know that Wilson line with R and R bar each give us 1. So this state is R bar sum over all. That is happy.
And then the only issue is that to literally get log K, the weight of each representation should be the same.
And that is the doubt because there's exactly one singlet when you put an R in that.
No, that I agree, but that the coefficient of that is the same regardless of.
That is by Rao's law because the inner product is putting a Wilson line with R and a Wilson line with R. Now you're asking what is the partition function of one Wilson line with R and one? And there's exactly one state in the middle of space. The least of it, right? So the answer is 1 for all. In fact, this now calculates this way, right? You compute it by relating it by surgery to yeah, I think the way Witten would do it. It would take this, not right on this way. It takes this, cuts out 1 and then resurgery to make it 2.
Because the surgery would be now on a sphere which goes.
No, this surgery on the boundary of the,
Just along one of the surgery. No,
Yeah.
the boundary of surgery on the boundary would never change the type of slice. Would never change.
Which one? This one?
You make a move. You want to take a rhythm of this one. That would involve cutting out a ball with 4 it's the last line in that. These two representations, and you can see that there is one when I do S transformation yeah, but it's the left hand side which we are essentially computing S2 times S1 and 3 into
Yeah, so for this Hoflink we have maximum entropy. So this is like analogous to the Bell state in the information theory.
Your headmaster move is one of the extra. Yeah, that's a very good.
So there are some more results.
That's what we do.
Yeah, so this is the entropy is the log of the dimension of Hilbert space. This is true for all the groups for Hoflink, and we have tried to obtain this entropy for like large values of the level and the large values of rank. And
what are you computing now?
so
Renyi entropy for this.
yeah, this is the Renyi entropy for Hoflink, which is simply log of
compute the whole density matrix.
yeah. So the whole density matrix is identity, the reduced density matrix,
Okay.
and the Renyi entropy is simply log of the dimension of Hilbert space, and we can study its expansion for like large values of k for classical Lie groups of finite rank.
Just like how many irreducible references, how many
Yeah, by counting how many
integrable references.
integrable representations and doing expansion.
Okay.
And you can also do for the exceptional. This is for the exceptional Lie groups, large values, and so.
Why is the large K limit particularly interesting? Do you have a semi-practical expectation for the large K limit?
So we expect that probably this the large K values of integral entropy will be somehow related to some volume, like your limit of the Jones polynomial gives the volume of the knot complement.
Classical dimension of what? Exactly.
Yes.
So that's infinite. So the answer is infinity. So the coefficient of complete. Exactly.
Yeah.
Exactly. Exactly. But for asking that you need a cutoff.
Yes.
So it's not entirely.
Yeah, so this is the expansion. So there's asymptotic. So the Rayleigh entropy divided by log K goes as R, the rank of the group. Okay. And this is the expansion when the rank is large, but the Chern-Simons level is K is finite. This is the result when both the rank and the level are large, but their ratio is constant.
So this is like a token.
Yeah. Rayleigh entropy here. But the Rayleigh entropy here for Hopf-Link is independent of the Rayleigh index. It's a log of dimension of Hilbert space. No, this is the Rayleigh entropy.
Trace rho to the K. Here rho is constant. So it doesn't matter what
K is the Chern-Simons level. K is the Chern-Simons level, and I have the definition here. So this is the Rayleigh entropy. Alpha is the Rayleigh index. Yes. Yes. So for Hopf-Link,
is your any rho square or rho to the n?
rho to the power alpha. This one. For Hopf-Link, yeah. So for Hopf-Link, the Rayleigh entropy is independent of alpha. This is the result. So yeah, using the property that this is unitary, we can compute the entropy here, and this is log of dimension of Hilbert space for any alpha.
Wait, you said that the density matrix was proportional to identity. Is this correct?
The reduced density matrix.
Reduced density matrix? So
Yeah.
now this is convex flow. If the density matrix is proportional to identity, but trace of density matrix is 1, then the density matrix must be 1 over dimension times identity.
Yeah, so
Sorry, so in 1 over dimension, for that, the Rayleigh entropy
so it will be like 1 upon.
It's independent variable.
Yeah, so this times identity matrix, which is a
Yeah.
BH.
So now if you don't mind, can you just compute the Rayleigh entropy to the power alpha?
You're right, maybe 1 minus alpha will cancel it.
Yeah, so
Okay,
Yes,
so
sir.
it's dh to the 1 over
yeah, it will cancel out.
Because you get an extra dh on the trace.
Yeah. You're right.
So this is done. Yeah, so now we have some results for 3-component links. So this is some 3-component link, and if we compute the entanglement entropy for this case, we find that tracing out any of the knots in this link gives a separable reduced density matrix on the other two knots. So this link is sort of an example of the GHZ-like state.
The separable reduced density, what does that mean?
Yes. Yeah. So if you trace out one of the knots, the entropy is 0.
Oh.
Yeah. So the state on the remaining two is a separable state. I think so, yes. So yep. Borobin ring is this one. Yeah.
So here you would expect that property because if you remove one, you get immediately.
But this here is non-separable.
Uh,
because in the previous case, in the still you keep the linking, but you're saying it's still not.
Is it the other way around? Okay.
Now, even the trefoil, if you remove non-trefoil, whatever, you got a non-trivial entropy. But if you remove one, you find it. So some of the equation is not working.
Okay.
Yeah.
Yeah, here we are tracing out one of the, if you just remove one of them by putting a delta, then it will give a.
Yeah, removing is like replacing it by identity.
Yeah,
Tracing is.
tracing is, yeah.
Difficult.
Nice to do that.
Yeah, I wonder if tracing is SQL to something.
Yeah, so this Borromean rings has a double-like structure. Okay, so this is the question which you asked. So this is the case when this is like half link with the two circuits are linked n number of times, right? So the link state for this case is given like this, and this link state shows a periodic entanglement structure in n. Actually, this comes from, mathematically I can see that this comes from these matrices, because for a finite k, these are like periodic matrices, right? For any? Yeah, this is true for any group.
And what is the periodicity then?
Yeah, this is the, yeah, so this I have given an expression. This is the T matrix. And for a finite y is the dual Coxeter number, and finite level k, the T matrix has a periodic nature, right?
With what periodicity?
Yeah, so periodicity for,
XUN was the
I have given here,
more of an answer than
for SUN k, the periodicity is n times n plus k. No, this is not framing. This is not framing. So framing will be like if you take twist in one of the circles, right? That will be framing, and these entropies do not depend on framing. So large scale limit of I guess there will be no periodicity if you take k goes to infinity. Yes.
As a function of n, and then take the level to infinity. Last time we
are talking about entropy or the periodicity?
They calculate the entropy
Uh.
and then ask for if what happens with the K goes to infinity.
Hmm.
How does it depend on this?
So for each, so in order to compute entropy, you first have to fix n. Okay. For example, Hoflink is n equal to 1. So for this, you can compute the entropy and take the k goes to infinity limit. Then you can compute for n equal to 2, compute the entropy and take the k goes to infinity limit.
At K goes to infinity limit, first one goes like log K.
Yeah. So
Second one.
So for second one, actually this it's very difficult to get the large k behavior, because for k goes to infinity, all the representations are allowed. So we are not able to explicitly sum over all the representations. So we don't have any closed form for general n. Huh? For n equal to 2, we have the yes. So yeah. So here entropy was some finite number for k equals to infinity, but beyond that we don't have the result for.
And which representation were you mean?
Here? No, you have to.
When you say that for this periodicity?
So that depends on your level k. Depending on level k, you have certain.
This was the periodicity for the entanglement.
Yes.
So this must, okay, I'm going to give you a conjecture. You see, suppose I take two representations, R1 and R2, and I take one of them around the other, you get an R0 phase. You're taking this n times R. So you're getting n copies of this R0 phase. So you can ask now, if you vary over all integrable representations, what is the minimum number of loops you have to do such that any two pairs will have R0 phase 0, identical? That will be the set.
Okay.
This is my conjecture. It's not real.
So this number is like, then you will not even detect classical. There is no phase. You can take any two representation and.
But in your case, k goes to infinity and n goes to infinity together. You can do something that sort of that. Right, because that's what it should be, right? You're saying, when is it not sensitive to the fact that you've gone it up? That's the statement that you're not sensitive to one particle going around the other. That's the statement that the effective anionic phase of any two particles going around the other should be nothing. Now clearly if you go enough times, because there's a finite number of phases, you will get that. And this must be the number of times you get it.
And what about different groups?
What?
If you choose different groups,
Any group, this works for any group. You see, suppose I take any two representatives, R1 and R2. If I take R1 around R2, I get some phase. Okay? Now, I will have to think, but I think that these phases will all be rationally related to each other. Because the denominator is always the same.
So this is the phase which you get, right?
So that's what you're saying, right? Yeah. So because you're computing the entanglement entropy, you're summing over all possible representations. So you want the minimum number of windings such that any representation with any other has no phase. If such a thing exists, it must be this.
So this is saying like this, right?
This is what it is. Now you're saying, if you have 3 particles, 4 particles, it's interesting. I wonder if it will ever happen. But yeah, it would be something similar. That you would have to have. Maybe we could after the talk formulate a precise thing. Then I decide.
So if I take the two things, large K and large N,
some representations still have not to do it. So this is the question becomes easier to answer. The key layer is the sum of all that.
It doesn't depend on the framing, because like Jones polynomial depends, but it will give a so yeah. So if you take a twist in one of the circles, It will be a simply framing factor, right? So some and no, the entropy is independent of the local framing, right? Local unitary operations. So doing a framing is like a yeah. So this is the periodicity. So this is the so this is the von Neumann entropy, Renyi entropy with index 1, and we have computed for various values of n, and this is the group SU2 with level k. K is equal to 3. So n equal to 1 means the Hopf link with one twist. So the entropy is log 4 because the dimension of Hilbert space for SU2 3 is 4. For n equal to 2, this is the value of the entropy, and you can see here that there is a periodicity. The periodicity is 10. Okay. For n equal to 10, the entropy becomes 0 and then again starts repeating. So for this group SU2 with level k with level 3, the periodicity is 10. So in general, the formula for periodicity is for SUN group with level k, the periodicity follows this pattern. Yeah, so entropy becomes 0 when this the T to the power n matrix becomes, yeah. Okay, and so this is another result in this paper. They have tried to interpret this entropy like similar to Ryu Takenagi result. What they are saying is that the entanglement entropy between the two sublinks gives a measure of the topological obstruction to the splitting of the link between the two sublinks. For example, this is an example of two unlinked unknots. So you can try to separate these two unknots by putting a sphere in between. So they are trying to put a minimal genus surface so that we can separate the two components of the link. Okay. So these two links can be separated using a sphere. This is a Hopf link which can be separated using a genus 1 surface, and this is some complicated link which can be separated using genus 2 surface. Right. And using this, right. So, but this is the minimum genus. You can also put a torus here to separate, right?
So you are saying that entropy should just be the dimension of the Hilbert space on that?
No. So the entropy follows this this bound. So this is the bound. This is a simpler bound. So the bound depends on the genus of the minimal separating surface. Okay. So. So this is a direct quote from this paper, and they try to say that this is similar to the Ryu Takenagi, where you have the entropy is related to the surface area of some. Okay. So
what I'm not understanding is why it's log. You might have thought that if you could break up the thing into two parts.
Hmm.
The log of the dimension of Hilbert space
Yes.
on the genus.
Yes. And and that product is the log.
This is the dimension, right? So this is the dimension of Hilbert space for a genus.
Oh, okay.
Yeah.
Right?
Yeah.
For SU2, this is the dimension.
And what happens at -2?
Which -2?
So if you take the log of that, you get.
So from here to here, they have used this condition that S0j is always greater than or equal to S00 for any j. So they have tried to relax the bound and get this result.
I can, and there's some half between them. There's 2 min g. Oh, that a log to the -2. So yeah, fine.
Yeah. I think this is the Valinde formula for SU2 group. Okay. Now there are some questions which we would like to answer as possible. So we have already done, this computation has already been done, 2 component, which gives a Hoffling is a Bell state. We also have results for 3 component where we have G, Z and W. And we want to know if it is possible to study the entanglement classes for 4 component links. There is for a 4-partite system, the classes are not known. No, it's the classes are not known. So classes. I think it's a measure of the separability of the system.
What are the 2 classes of interaction where one, when you trace out one, you get it disconnected or not? You get the 0 entanglement or not?
Yeah, that's the class. Yeah.
And the W class is based on one of
So both these classes are like maximally entangled, but depending on whether tracing out one part gives a separable density matrix, gives 2 classes.
Classes of maximally entangled systems.
Yes. In 4-partite system is not known.
Maximally entangled means any one system with the other 2 is maximally. That's what you mean by maximally entangled? Right. That the entanglement entropy of one system with the other 2 is the dimension of the Hilbert space of that one.
that is not clear here.
What do you mean by maximally entangled? What is maximally entangled?
If the density matrix is some multiple items.
Right.
That is like saying the dimension of Hilbert space.
Yeah.
That is not true for
Yeah.
See, that if you trace out one of this, the remaining 2, whether they're maximally entangled or
Yeah, you could do this. You could trace out 2 and look at the density matrix for one of them. And demand that that is maximal entanglement. Now you could then trace out 1 and ask about the entanglement of the remaining 2. I thought that's what you would do. That is the class. But the class is defined for things such that once you trace out 2, you're left with dimension of Hilbert. Is this right?
Yes, yes.
Maximum that is I am not committing to the dimension.
That is true, right? That is true.
It does not seem to be democratic between among 1, 2 and
No, I mean this is clear. Here you can see that
there is a statement about the GAC which is that
no. Here you can see that
without any
if you just if you remove this not 2, 1 and 3 are still linked. But here if you remove any of the components, this whole thing will be separated. Right?
Yeah, no, I was getting the drawing. I mean,
Okay, so the second question is try to look at the volume conjecture. The volume conjecture is simply tells that the limit of the Jones polynomial for a hyperbolic knot is related to the volume of the hyperbolic volume of the knot complement. Right? So here our entanglement entropy is like sum over the Jones polynomials. So one can ask what happens when we take k goes to infinity limit of this entanglement entropy. Is it related to volume of some surface similar to the volume conjecture? And the recent result, they computed the entanglement negativity for some links, and they show that if you have a torus link, the hyperbolic volume for the torus knots and torus links is 0. So if the link is torus, then the entanglement negativity is also 0. So we think that negativity can be a good candidate for this conjecture. But we need to compute this negativity for large scale.
I don't even know what entanglement negativity is, but it's not important.
And another question is, what happens if we try to complexify the gauge group in this setup? So like if we put SL2C. So we know that the SL2C Chern-Simons on the solid torus gives a BTZ black hole. So I mean, we don't know if and the entropy computed in this setup can be somehow related to the black hole entropy.
So just from the field theory point of view, if you just try to understand what SL2C Chern-Simons theory is, forgetting about anything else, is this well understood? For instance, will you get infinity if you try to compute the partition function on the torus?
The Hilbert space is definitely infinite dimensional.
Okay. So can you compute everything you want to compute in this theory? Just a question out of the not trying to fight you. I just don't know. Have people computed things for SL2C Chern-Simons theory following this theory?
Not for a general manifold. For solid torus, it's computed.
What is computed?
The partition function.
So that's infinity we just said. There's a number of representations. Oh, no. Yeah, why isn't it infinite? So I'm talking pure infinite.
The Hilbert space is infinite dimensional. Okay. For trefoil. Oh.
No, but what about just torus partition function? T2 times T3 partition function. Is that infinity? Yeah.
Oh.
Okay, so it would be great if you could explain a little bit about that. How does that work? Usually this partition function counts the number of integrable representations. Is that infinite or not? In this case.
The Hilbert space is infinite dimensional, but
Therefore, the
representation.
partition function on T3 is
why should it be infinite?
because it's computing the dimension of Hilbert. Well, it's a topological space. All states are zero. Okay, later.
The kind of the appearance of SL2 in complexified two dimensional in the context of this slightly roundabout field theater responses, where you have a particular Chern-Simons theory defined on some compact three manifold, and when you increase on that, you
Yeah, so as of now, these are the questions which we are trying to figure out. Thank you.
One quick question. If we do like something like an SL2C Chern-Simons theory, do we need to specify? Do we need to specify some boundary condition at infinity in this case?
I don't know.
I mean, manifold is the group manifold is not compact. That's an infinity. So to make the problem well defined, you need to specify what's going on. Maybe many different ways of defining.
Yeah, you can do that in terms of this because the chip symbol is always one. Because they're going all the way down always. So you can measure as appropriately determines action. Then you can focus on that. And then the idea would be to identify the homology, the right homology of the real cycle in terms of the and then you stand in at the one point. That's the conceptually.
Yeah. I was thinking in the following context. Suppose we took SL2 whatever times SL2 whatever, and we were saying that we do AES 3. Then in AES CFC we would be doing the path integral with particular boundary conditions at infinity, namely that is asymptotically AES. And that's a very important part of doing AES. Putting those on. So that would be, for, at least for me, one of the most interesting applications of it. And I would wonder how you do it.
Then the path integral will be functional of the boundary.
Functional of the boundary.
Yeah.
Right.
So that has, for example, been computed by torus and so on in the ESCFT context and been matched with the CFT partition. Where you have this, the boundary terms appearing, etc., which depends on the boundary matrix.
And has Petrov done this classically or quantum mechanically?
It's classic. It's classic, not
Classic. But it would be interesting since Chern-Simons is a solvable theory. One could do that quantum mechanically.
Yeah, that's all the idea.
Yeah. But if one could marry that with just pure Chern-Simons already, get something interesting out of that, maybe something interesting. I mean, given that Chern-Simons is pure gravity, at least in some sense, some way.
But your question about the boundary condition will remain. I mean,
Will remain.
it will be a function of the boundary condition.
So you will have to understand how to do this thing
In the maybe the kind of boundary condition will be
as a function of boundary.
different stuff with some boundary condition.
Maybe that will choose out the most natural, maybe undeformed.
So is it mean that the boundary of radius is the boundary in this time space? I mean, it's a non-compact group manifold.
Yeah.
Boundary of radius and boundary of
Not related, right?
I mean, some solutions can be written as an expansion of the connection in 1 by rho. And I'm not sure anything has to do with the boundary of this case in that.
It's not. Well, let's see. So what is the relationship between, so the relationship of AES3 to the group is sort of like the relationship of S3 to S2 tendency. So we could ask what is the relationship of S3 to S2 tendency? to infinity of in this body term is somehow related to going to infinity. We could make that more precise. I think maybe I'm wrong. You don't think so? Probably. We're not going to be expert.